Welcome to our deep dive into DINOv2. You sent over a whole bunch of research papers on this one, so it looks like you're ready to get into the really technical details of this AI vision breakthrough.
We are indeed going pretty deep today, especially into the architecture.
Oh, cool.
DINOv2 stands for, get ready for this, distillation of knowledge with Supervision v2. Quite a mouthful.
Yeah, it is a mouthful.
But it's making huge waves in the world of self-supervised learning when it comes to computer vision.
And from what I understand, it's kind of like teaching AI to see the world more like we do.
Right.
Like recognizing patterns and objects without having to have all those labels.
Yes.
Kind of like how a kid learns just by looking around.
Yeah, that's a great analogy, actually.
Cool.
Because the idea behind foundation models in computer vision is all about making systems that can learn these like really fundamental visual concepts,
Yeah.
but from just raw data, so no labels.
Wow.
It's like we're trying to create, the visual equivalent of all those large language models that have just totally revolutionized NLP.
Okay, so instead of needing like captions or text descriptions to learn, DINOv2 is just straight from the pixels.
Exactly. So we're moving away from this text-guided pre-training, which is a big deal.
Huge.
Because now we can train on these massive data sets of images that are already out there.
Right.
And we don't have to spend tons of time and money labeling everything. It's really exciting.
So it's just learning from what's already out there in the world, which is kind of how we do it too.
Exactly.
Now, I understand that DINOv2 uses this self-supervised approach, something called discriminative learning.
Yeah.
Can you break that down a little bit?
Of course. So in discriminative self-supervised learning, the model is basically learning by figuring out the differences between images, even different parts of the same image.
Okay.
So imagine you show it two different crops of the same image.
Yeah.
It has to learn how to recognize that those two pieces are actually from the same source, even though they look a bit different because of the angle or the scale.
So it's learning to recognize that even though they look different, they actually are the same thing from different perspectives.
Yeah,
That's
exactly.
pretty neat.
It is.
So let's get into the architecture of DINOv2.
Okay.
What are the key components that make this thing tick?
Well, DINOv2 is built on the strengths of these older self-supervised models, like Dino, of course,
Right.
and IBT, and it kind of combines them in a new and interesting way.
Okay.
It's got these two main objectives, an image level 1 and a patch level 1.
Let's start with the image level objective.
Okay.
How does that work?
So that one takes inspiration from the original Dino model, and it uses this student-teacher framework where you have a student network that's trying to copy what the teacher network is doing.
Okay.
The teacher network sees the whole picture while the student only sees a cropped part.
So it's like the teacher is showing the student different pieces of the puzzle and helping them to see the bigger picture.
Yeah,
I
exactly.
like that.
So by making the student match the teacher's output, the model learns to create similar features for different crops of the same image.
Okay.
And this happens by minimizing what's called a cross-entropy loss between the features that the student and teacher make.
Right.
But here's the thing. It focuses specifically on something called the class token of a vision transformer, or VIT.
So this class token thing, that's interesting. It's
Yeah.
like a summary of what's in the image, right?
Yeah, you can think of it that way. It's like the essence of what's being shown.
Okay.
And by using that for the cross-entropy loss, DINOv2 basically forces the student to learn a more global understanding
Yeah.
like the teacher has.
So that makes sense. So it's getting like a high-level overview of the image.
Yeah.
Okay, now what about the patch level objective? How does that fit in?
Right. So that one's inspired by iBot, which is really good at picking up these small details in images.
Okay.
And in this objective, the model tries to rebuild masked patches by predicting features of the visible patches from the teacher network.
Okay, so it's kind of like a jigsaw puzzle where it has to fill in the blanks based on what's around it.
Exactly. It has to really pay attention to the little details and learn to represent them accurately, even when some info is missing.
And that's really important for stuff like semantic segmentation.
Yeah, exactly. Or depth estimation, things that need pixel-level understanding.
Yeah. So by combining these two objectives, DINOv2 is learning to see the world both broadly and in detail.
Yeah, big picture and small details.
That's pretty cool.
It is, but it doesn't stop there.
Okay.
DINOv2 also has some new tricks up its sleeve.
Like what?
Well, one big innovation is how it handles the projection heads for the Dino and iBot losses.
Okay.
Instead of using the same one for both objectives, it uses separate ones. They're untied.
So what's the advantage of having separate projection heads?
It's like giving each task its own special set of tools.
Okay.
So the features learned for image-level discrimination don't have to be limited by the needs of patch-level reconstruction, and vice versa.
So it's all about making the learning process better by allowing the model to create more specialized features.
Exactly.
That's smart. What else is new?
Another cool thing is using something called Sync-Horn-Nop centering for feature distribution.
What is that?
It's a bit technical, but basically it helps make sure that the features the model learns are more evenly spread out.
So it's like preventing it from getting stuck in a rut and only learning about a few things.
Yeah, exactly. We want it to explore a wider range of visual concepts.
So it's got to keep learning new things.
Yes.
What other innovations are there?
Well, there's also this thing called a colio regularizer.
Okay. And what does that do?
It's another little nudge to help make the feature distribution even more uniform.
Got it.
So we're making sure it captures lots of different visual ideas and doesn't just get fixated on a few dominant patterns.
Right. Makes sense.
And lastly, they added a short training phase, but with higher resolution images.
Oh, interesting.
This really boosts performance on tasks that need really detailed pixel-level understanding, like semantic segmentation.
So you train it on the basics first, and then you give it like a high-def upgrade.
Exactly. It sharpens its vision after it's got the main concepts down.
Gotcha. So all of these architectural innovations are super interesting.
They are.
But I'm also curious about like the practical challenges of training such a complex model.
Yeah.
I imagine it takes some serious computing power to handle all that data.
You are absolutely right. Training these large-scale models like DINOv2, especially on huge data sets, is a real challenge.
Yeah.
But the researchers have come up with some pretty ingenious solutions.
Okay, let's hear. What did they do?
Well, one of the biggest bottlenecks in training these transformer-based models is the attention mechanism.
Right.
It can be very computationally expensive and memory hungry.
Yeah, I can imagine.
So DINOv2 tackles this by using something called flash attention,
Okay.
which is designed to make attention much faster and less memory intensive.
So it's like they optimize the way the model focuses on different parts of the image.
Precisely.
Smart. What other tricks do they use?
Well, another clever technique is called sequence packing.
Sequence packing. Okay.
Remember how Dino uses different image crop sizes?
Right.
This actually leads to sequences of different lengths, which can be a pain to process efficiently.
Makes sense.
So sequence packing comes in and basically combines these different length sequences into one big one.
Okay.
This allows the model to process them all together like they're the same length.
It's like packing different size boxes into a bigger container to make shipping easier.
Exactly. A simple but very effective solution.
Yeah, that makes sense.
And they've even optimized the way they use stochastic depth.
Oh, right. Stochastic depth. Remind me what that is again.
It's a technique where you randomly drop parts of the model during training,
Right.
which helps the model generalize better.
Gotcha.
But DINOv2's implementation is even smarter.
Okay.
It completely skips calculating the parts that are dropped.
So it saves time and energy.
Exactly. It's like saying, hey, why bake the whole cake if we're only going to eat a slice?
I like that analogy.
It's about being efficient.
Makes total sense.
Now, you might be wondering about those smaller DINOv2 models.
Yeah. How do they manage to perform so well without all the fancy stuff of the giant VITG model?
Well, that's where model distillation comes in.
Okay.
Instead of training these smaller models from scratch, they get to learn from the big VITG model.
Okay.
It's like a master passing on their knowledge to an apprentice.
That's a good way to put it.
So they get a head start in the learning race.
Wow. So it's not just about making bigger and bigger models, but also finding ways to share that knowledge with smaller, more practical ones.
Exactly.
That's fascinating. So we've covered a lot in this first part of our deep dive into DINOv2. We've talked about foundation models, self-supervised learning, the nuts and bolts of the architecture, and even how they made it all work efficiently at scale.
We've definitely laid the foundation for understanding this impressive advancement in AI vision.
I'm ready to learn more.
Well, in the next part, we'll explore how this really sophisticated architecture translates to real-world performance across a whole bunch of different benchmarks.
Sounds good. I'm excited for that.
Me too. It's going to be good.
I can't wait. Join us in part 2, where we put DINOv2 to the test and see how it stacks up against the competition.
See you there. Welcome back to our deep dive into DINOv2. So last time we really dug into the model's architecture, all those really neat training techniques.
It's fascinating.
Yeah, it really is. It's amazing what they've done to allow DINOv2 to learn so well from images that don't even have labels.
Right, using all that data that's already out there.
Exactly. And now it's time to put this powerhouse model to the test.
Yes, let's see what it can do.
All right, so you mentioned that DINOv2 performs really well across a variety of benchmarks.
Yeah, it seems to be pretty good at a lot of things.
It does, and I'm eager to share with you the specific tasks where it really shines and how it compares to those other state-of-the-art models.
Yeah, because as AI scientists, we really want to know if it lives up to the hype.
Absolutely. So let's start with image classification, which is a classic benchmark for evaluating how well a model can learn visual representations.
Right, it's like the bread and butter of computer vision.
Exactly, and for this we'll use the ImageNet-1K dataset, sort of the proving ground for these models.
Okay, so we're talking about the task of, looking at an image and correctly labeling it with its category.
Right.
Like saying that a picture of a cat is a cat, that kind of thing.
Exactly, and that's fundamental to so many different applications in computer vision.
Yeah, absolutely. So how does DINOv2 handle this?
What's really remarkable is that it achieves these impressive results on ImageNet without any fine-tuning.
Wow, no fine-tuning at all.
None. We just take the pre-trained model, freeze it, and then train a simple linear classifier on top of the features it's already learned.
Okay, and that's called linear evaluation, right?
Yes, exactly. It's a standard way to assess the quality of the learned representations.
So we're basically asking how well can this model separate different categories just based on what it's learned from those unlabeled images.
Precisely, and the results are really quite compelling.
Okay, I'm intrigued. Tell me more.
So DINOv2 consistently outperforms other self-supervised models on ImageNet, even those with similar architectures.
That's impressive.
And get this, it even beats the performance of some weakly supervised models.
Wait, really? So models that have actually been trained on some labeled data?
Yes, which you would think would give them an advantage.
Absolutely. That's a huge achievement.
It is. It really highlights how effective DINOv2's self-supervised approach is.
So it's learning something truly fundamental about visual information, even without being explicitly told what things are.
Exactly, but ImageNet is really just the tip of the iceberg.
Okay, there's more.
Oh yeah, DINOv2's real strength lies in its ability to generalize beyond this single data set.
Now that's what I'm really interested in. Because we need models that can handle all sorts of different tasks, the complex challenges we face in real-world applications.
Absolutely, and one area where DINOv2 really shines is fine-grained classification.
Fine-grained classification, okay.
This means being able to tell the difference between things that look very similar, like different species of birds or types of flowers.
Right, like distinguishing a daisy from a dandelion.
Exactly, those subtle differences that are really hard even for humans sometimes.
Yeah, it takes a keen eye.
And DINOv2 is remarkably good at it.
Wow.
On data sets like iNaturalist and Places 205, which are specifically designed for fine-grained classification, it achieves state-of-the-art results.
So it's beating models that are specifically designed for those tasks.
Often, yes, even models that have been fine-tuned for those specific data sets.
That's incredible.
It really suggests that DINOv2 is learning something more sophisticated. It's not just recognizing broad categories, it's understanding those finer details.
So it's developing a much deeper understanding of visual concepts.
Exactly, one that we can apply to a much wider range of problems.
That's really exciting.
And this ability to generalize extends to instance recognition as well.
Instance recognition.
Yeah, so this is about recognizing specific landmarks or artworks, or even being able to match street view images to old photographs.
So it's not just about recognizing a category of object, it's about recognizing a specific, unique instance.
Precisely, like recognizing the Eiffel Tower from a certain angle, or a particular painting by Van Gogh.
That's a different kind of visual intelligence.
It is, and once again, DINOv2 delivers.
Okay, I'm on the edge of my seat. Tell me more.
On benchmarks like Oxford and Paris, which focus on landmark recognition, it significantly outperforms both self-supervised and weakly supervised approaches.
It's remarkable how well this model can generalize to such different tasks. It's like it's developing this intuition, like how humans learn to recognize things.
Yeah, that's a really interesting observation, and it raises some really deep questions about what it means for a model to truly understand the world.
It does. It's fascinating.
It is, but before we get too philosophical, let's move on to another area where DINOv2 excels, dense prediction tasks.
Dense prediction tasks. Okay, now we're getting into the really challenging stuff.
We are.
This is about understanding images at a much finer level, right?
Exactly. So in dense prediction tasks, we're talking about assigning a label or a value to every single pixel in the image,
Okay.
like in semantic segmentation, where we label each pixel with the object it belongs to, sky, grass, building, that sort of thing.
It's like coloring by numbers for AI, but instead of just recognizing an object as a whole, it has to understand the boundaries of each object at the pixel level.
Exactly. And DINOv2 has achieved some remarkable results in semantic segmentation.
Really?
Yeah, it's often comparable to, or even better than, models that have been specifically trained for that task.
So it's learning to see the outlines of things without ever being told what those things are.
It's incredible.
That's amazing.
And it doesn't stop there. This ability extends to other dense prediction tasks as well, like monocular depth estimation.
Monocular depth estimation. Okay,
Yeah.
remind me what that is.
So that's where the model predicts the depth of each pixel in an image, essentially creating a 3D representation from a single 2D image.
So it's not just recognizing objects, it's learning to perceive depth and spatial relationships from a flat image.
Exactly. And that has huge implications for things like robotics and autonomous navigation.
Because for robots to interact with the real world, they need to be able to understand how far away things are.
Precisely. DINOv2's success in monocular depth estimation is opening up some very exciting possibilities in robotics.
This is also impressive. DINOv2 is really pushing the boundaries of what's possible with self-supervised learning.
It really is, and its performance on these benchmarks is a testament to the power of this approach.
But I'm curious, beyond just the numbers, what kind of qualitative insights can we glean from this model?
Now that's where things get really interesting.
Okay, ready.
So the researchers went beyond just those standard benchmarks and did some fascinating analysis to explore the model's internal representations.
So like peeking under the hood to see how it's actually seeing the world.
Exactly, to see what kind of knowledge it's extracting from the data.
And what did they find?
Well, one of the most revealing analyses involved using principal component analysis, or PCA, on the patch features that the model extracts.
Okay, in PCA, that's a way to visualize the most important dimensions of the data, right?
Right. It's like finding those hidden patterns that the model is using to make sense of everything.
And what did those patterns reveal?
Well, they found that the first principal component, which captures the most variation in the data, consistently separates foreground objects from the background.
Wow, so it's figured out how to identify what's important in an image, like the main subject, without ever being explicitly told.
Exactly. It's like a photographer who instinctively knows how to compose a shot to emphasize the most important element.
Yeah, that's a great analogy.
And it gets even more interesting. The other principal components seem to correspond to meaningful parts of objects.
Okay, like what?
So, for example, when they looked at images of cars, one component might represent the wheels, another the windshield, and so on.
So it's breaking down objects into their parts, like it's building a hierarchical structure of the visual world.
Precisely. And this is something that just emerged from the training process. Nobody programmed it to do that.
It's amazing. It's like it's starting to understand the visual world in a way that we haven't seen before.
Yeah, it's not just recognizing patterns, it's grasping the relationships between objects and their parts.
It's truly remarkable.
And this understanding is further supported by another analysis they did called patch matching.
Patch matching. Okay, how does that work?
So in this analysis, they compare patch features across different images.
Okay.
And they ask the model, can you find similar regions or parts in these images?
So it's like a visual matching game, but across different images and even different categories of objects.
Yes, exactly.
And can it do it?
It can, and what they found is that DINOv2 can match semantically similar regions even when the images are very different.
Like,
for example, it might match the wing of a plane to the wing of a bird.
wow, so it's recognizing that they have the same function, even though they look completely different.
Precisely. It's learning something fundamental about the concept of a wing, not just specific instances of wings on birds or planes.
It's developing this abstract understanding of visual concepts that it can then apply to new situations it's never encountered before.
Exactly, and that's what's so mind-blowing about these patch matching results. They show the model's ability to transfer its knowledge across different domains.
It's incredible. It really feels like we're on the cusp of something truly groundbreaking, like AI is starting to develop a visual understanding that rivals our own.
I agree. It's a fascinating area of research, and it's moving so quickly.
I can't wait to see what comes next.
Me too. It's a very exciting time to be working in AI.
And in the final part of our deep dive, we'll explore the broader implications of these advancements and consider the potential impact of DINOv2-like models on all sorts of fields and applications.
Yes, we'll delve into the amazing possibilities that DINOv2 unlocks and discuss the challenges and opportunities that lie ahead.
Sounds good. Join us for part 3, where we'll wrap up our exploration of this amazing model and consider its impact on the future of AI. Welcome back to the final part of our deep dive into DINOv2. It's been quite a journey.
It really has. We've gone through this incredible architecture, looked at all the amazing things it can do,
Yeah.
and even sort of peeked into how it's learning about the world.
Right. It's almost like it's developing its own visual understanding.
It is. It's fascinating.
So now I think it's time to step back a bit from all the technical stuff and look at the bigger picture.
Yeah, good idea.
What are the implications of all this? How could models like DINOv2 actually change things out there in the world?
Well, the possibilities are just huge and incredibly exciting.
I bet. And for AI scientists like us, this has got to be a game changer.
Oh, absolutely. So we've seen how good DINOv2 is at things like image classification, object detection, even figuring out depth.
Right. It can do a lot.
Yeah, but where could this technology really make a difference, like real-world applications?
Yeah, that's the big question.
It is. And, one area that's just ripe for disruption is robotics.
Robotics, okay.
Yeah, imagine robots that can easily navigate through all sorts of complicated environments. They can handle objects really skillfully.
Yeah?
And they can even interact with humans in a way that feels natural and intuitive.
It's like robots that can actually see and understand the world like we do.
Exactly, and it's something we've been dreaming about for so long.
Right, it's like science fiction coming to life.
It is, and DINOv2 is bringing us closer to that.
How so?
Well, its ability to understand depth, to recognize objects and their parts, and even to apply what it's learned to new situations.
Yeah,
That could completely change the game for robotics.
I can see that.
We could have robots assisting in surgeries, doing dangerous work in hazardous places, maybe even helping out with chores around the house.
It's like giving robots a whole new level of perception. They'd be able to do things that were just too complicated or too risky before.
Exactly. It's like giving them a superpower.
That's a good way to put it.
And it's not just those big industrial robots or specialized ones either. Think about assistive robots.
Right, for people with disabilities.
Yeah, DINOv2 could have a huge impact there, helping people to be more independent.
That would be amazing.
Imagine a robotic arm that can help someone who has trouble moving to eat, get dressed, or even do things like painting or drawing.
Wow, yeah, that's really inspiring.
It is. It's using AI to actually improve people's lives.
Okay, so robotics is one area. What else?
Oh, there's so much more. Think about image editing,
Cool.
content creation, even things like medical imaging. All these areas could be transformed by DINOv2's ability to understand images so well.
It's like this multi-tool for anything visual.
It is. Imagine being able to edit pictures with incredible precision and control.
Right.
You could change objects, fix backgrounds, even create entirely new visuals, all guided by this deep understanding of the image.
It sounds almost like magic.
I know, but it's becoming a reality.
That's incredible.
And then there's medical imaging, which is so important for diagnosis and treatment.
Right.
DINOv2 could help doctors spot those really subtle signs of disease in scans, which could lead to earlier diagnosis and better outcomes for patients.
It's like having an AI doctor working alongside human doctors.
Yeah, like a second set of eyes that can pick up things we might miss.
That's incredible. The possibilities really are endless.
They are, but with any powerful technology, we need to be careful, think about the potential downsides as well.
Right. It's all about responsible development and deployment.
Exactly, because AI is a tool, and like any tool, it can be used for good or for bad.
Absolutely. We need to be aware of the ethical implications.
Yeah, make sure it's used to benefit everyone, not just a few.
Right. So we need to address things like bias, fairness, transparency, make sure these powerful models aren't used to harm people or make existing inequalities worse.
It's a responsibility we all share. Researchers, developers, policymakers, everyone.
We all need to work together to make sure AI is used in a way that aligns with our values.
Couldn't agree more.
Well, this has been an amazing deep dive into DINOv2.
It has...
We've explored this incredible technology, seen what it can do, and even thought about its impact on the world.
It really shows the power of human ingenuity and the potential of AI to change things for the better.
And I have a feeling this is just the beginning.
I think you're right. There's so much more to discover in the field of visual representation learning.
Yeah, it's an exciting time to be working in AI.
It really is, and models like DINOv2 are leading the way.
It's been a pleasure exploring this with you.
Likewise, thanks for having me.
And to all of you listening, thanks for joining us on this deep dive. Keep exploring, keep learning, and keep pushing the boundaries of what's possible.
See you next time.